Hello, hello. The Tuesday teaching series rolls on with some more maths and Zoom. I thought absolutely nobody was going to watch that half an hour video on series and sequence the other day, but turned out it actually got a decent amount of views. So maybe some of you are finding it helpful. So here is some more maths. Right, so this week we are looking at questions that cover quite a broad range of topics. So you can see it's called Prob, Expo, and Calc, which is probability, exponential, and calculus. So if you don't do any of those topics, you can probably just stop watching now. A big thanks again to Brooke, who brought these questions to me, and Adrian, who ran through this lesson plan with me so that I can refine some of my explanations, as well as find out what things might need to be clarified for the average student. Not that I'm saying you're an average student, Adrian, you're above average. You know what I mean. All right, so just more maths teachings over Zoom today. Hopefully some of you out there find this useful. And if you haven't figured it out by now, from me repeatedly thanking Brooke for bringing these questions to me, we as tutors really appreciate when you guys work with us. So we do have the ability of just running our own lesson plans, but when you do tutoring, you don't want someone to just treat it like a classroom lesson, right? I'm thinking. So please help us out by bringing us the questions that you personally have problems with, or assessment notifications, my personal favorite thing. It really helps me to tailor my preparations so that we can get the specific assignments done as best as possible and things like that. So please work with us, show us what you're working on, and tell us which areas you want to improve on. And we will figure out a plan to help you get there. All right, on to the math. So we are starting with some quote unquote statistics, but this is actually probability. So this question is talking about a probability density function. And then there are several parts with that. So let's tackle them one by one. So here's a density function, and you should notice that it is incomplete. There is a k. 1 second, just get my Zoom pen. Annotate and the pen and red. Here's my pen. So there is a k in the function. So the function is incomplete. So your very first job is to figure out how to get that k value. This requires a specific, well, I'm not going back and editing this, so you can hear me mangling the words. This requires a specific piece of knowledge that the probability density function sums to 1. So here we go. So when you take the sum of all the different probabilities, so you have to remember the density function is the individual probabilities of the different scores. So this particular function have to add up to 1, because when you add up all the different things that can happen, that accounts for 100% of the probabilities. So the idea here is you take the area under the graph, or the sum, depends on how you want to think about it. So this particular probability function only exists between 3 and 6. So you take the sum between 3 and 6 of the primitive. I actually wrote this slightly wrong. I should actually be writing, oh no, this is right. Oh no, this is not. I should be writing the original function here, 36 minus x squared. And then you do the primitive when you do the whole square brackets thing. But Brooke and I were a bit pushed for time, so we kind of just took the easy way out and just read up the primitive straight away. So the primitive of 36 is 36x, and the primitive of x squared is x cubed on 3. And then you can actually put the k out the front, because the k is just a constant. And that's one of the laws of integration, is when a function has a constant multiplier out the front, you can take it outside of the integral when you evaluate it. So we want to get the value for k, so you're simply substituting 6 and 3 into this primitive function here, find the difference, and then divide both sides by that difference, because this is currently on the left. Right? So the key is you take the sum and you make it equal to 1. So the equal to 1 is the key part here. Right, so for the next part, I want to show the actual maths. I got some feedback that in the last maths lesson, there was too much time spent on the actual calculations. And that's fair advice. If you wanted to just jam stuff into your calculator, you can do that yourself. Pause the video and type it in. So I'm just going to be talking about the theory behind the problems, how to approach them. And then if you do want to try the calculations, you can get a pad and a pen and calculate them yourself by pausing the video. All right, part two, on the cumulative distribution function. So you can already see some of the notes here that I wrote for Brooke. The word cumulative means adds up. And then we want the sum of the area under the graph, and because that's what adding up means. But we are adding up the original probability distribution function. So we're not adding up this primitive. We're not adding up we're about to integrate. So I'll show you the actual working out. So here. Right. So here's the working out for that one. Oh God, that's still, sorry. Press the wrong button. All right, here we go. So image doesn't copy what? Let's try that again. This might not work so well. Let's see. It works. Okay. All right. So this is the particular working out. I'm just going to talk through the mentality and the approach behind it. And then if you want to do the maths, you can pause it and do the maths. So here we're taking the the cumulative function, which I'm going to call C of x, and it has a slightly strange presentation. You can see it's taking the integral between 3 and t, this extra parameter you are assigning. It's because we're trying to generate a function that shows the sum up to a certain point. So I'll show it to you in a graphical way. So the density function is an upside down parabola. So let's just say it's something like this. It might not be symmetrical. So it only exists between 3 and 6. So I should actually draw one that actually exists like that, maybe. It only exists between 3 and 6. And you know that from part 1, that when we sum this area here, this adds up to 1. Right? So all the different probabilities. So all the points on this graph are individual probabilities of the different events occurring. So in this case, it's like the lifespan of a termite, but the event doesn't actually matter. So this termite, if you want to find the probability of it living for, so let's say this is what? So 3, 4, oh, that's a terrible scale. 3, 4, 5. So let's say you want the probability of it living for 4.4 weeks, right? So you just take the 4.4 weeks, bring it up, and this will be the probability right here. So anyway, when you do the cumulative distribution function, you actually want a separate function that tells you this area for any value that you define. So let's say I want to find out the probability of the cumulative function of 5. So what that means is I need a function that tells me the area of this shaded part. So like how much total probability is contained for 3 weeks of life up to 5 weeks of life. So because we don't know how the user is going to use this function, like what point they want it up to, we need to define an extra variable t to be able to serve as the endpoint of how much space we are taking a accumulation of. So that's why this function has a very strange presentation of the integral between 3 and t. So as you can see my explanation right here. So what the sum of the area under the graph up to a certain point t, so 3 is now your starting point and t is now your endpoint. So when you actually do this function, you still take the primitive, so it's still this. So you take the, so this is the original function here, and then we know the k value now. So when we started, the question had an incomplete distribution function with an unknown value k. But from knowing the fact that it sums up to 1, we identified k through algebra. So after you have k, now that you have a complete distribution function. So we're going to integrate this from the starting point up to a point t. So you can see I kind of got lazy here. I just copy pasted some answers from the answers booklet. Oh, yikes. Okay, so you still take the primitive, so 36x and x cubed on 3. And you can see we are taking between 3 and t. And then multiply by 1 over 45, which is this number here. So we're actually taking it out of the integral and just doing this part here over here. So that's the function, and this is the primitive, and we're taking between t and 3. So once you do those things, you end up with something that looks like this. Now, this actually, going from the second step to the third step, is not the most obvious thing. There's actually something that's been applied in the official solution here. It's because you can probably spot it if maybe you like to pause the video and think about what happened going from here to here. All right, okay, so here's the answer. So you notice that the 145 actually became 1 over 135, and that is 3 times smaller. It's actually a smaller fraction. But here, all these numbers got 3 times bigger, right? So the 36 became 108, and the x cubed on 3 is just now x cubed. So what actually happened was they multiplied this bracket by 3, while they divided this fraction by 3 and keeping the entire expression exactly the same. This is not a required step or anything, but there is definitely merit to doing it this way because it allows you to get an x cubed term outside of a fraction. Because later on, you can see that this is our final, why did I write it twice? This is our final t function of the cumulative distribution function. And you really want t to be on its own with no fractions attached to it if possible. And in this case, it is definitely possible. So they took that algebraic approach. So they don't want x cubed, like, because when you substitute a t into here, instead of x cubed on 3, it will be t cubed on 3. So they did not want the t cubed on 3 in the final function. So they multiplied the interior by 3 while dividing the exterior by 3. So that's what happened between lines 2 and 3. And then there's just some more algebra stuff. So you can see this part here is this primitive with t substituted. And this part here is this primitive with 3 substituted. And then once you do all that, oh, this should be a 135, by the way, in case someone can explain to me why it shouldn't be. I feel like that's a typo in the solutions because you can see 135, 135, 135. It just brings it down. Like there's no reason why that should be 35. Anyway, all right. So once you do all the algebra, this is the final cumulative distribution function that you get. So which means for this particular function, you can substitute in any number of weeks that you want this particular term out to live, and it will give you the entire sum of the probabilities up to that week. So if you're substituting 5.5, it will get you all the probabilities from 3 and then all the way up to 5.5. So it's not just 3 or 4 or 5 because it's continuous. So it actually includes like 3.3 weeks and 4.1 weeks and all that kind of stuff. All right, so that is the second one. The third question is using the cumulative function, right? So find the probability that a termite's lifespan is greater than 5 weeks. So this part requires a bit of definitions awareness as well. Great. So I'll show you here. So the actual math is actually quite simple. So this is the math. P of x greater than 5 is equal to 1 take away the cumulative distribution function of 5. So again, with the previous function, so if whatever number you substitute in, it's all the probabilities up to that number. So if we take a sum of all the probabilities up to 5 and take it away from 100%, that gets you the remaining probability greater than 5. So you can see the math is quite simple, just requires you to understand what a CDF is and then using it to get part 3. So this is, again, a very kind hand-holding question where they take you from part 1 to part 2 to part 3. Generally, in the recent papers, I've seen that NASA is moving away from this style. They're actually moving to, here's an end goal. We want to see how you would approach it, which is a bit disappointing. I actually quite like this hand-holding style. I don't feel like it makes it any easier or anything. You still have to know the proper definitions of everything at that particular stage. But that is that question there. All right, moving on. This question is actually very similar, so I might skip. I'll just talk about the second part. So again, this is a probability density function. It's an incomplete one. It does have an unknown quantity p at the start. So the way you solve it, at least the way you solve the first part, is exactly the same as the way you solve the second part. So you make the function equal to 1, right? So you just got to realize that the sum of the density function, so the sum of the individual probabilities, have to add up to 1. And then you do some algebra, sub some stuff in, and you get 2/9. So let's talk about the second part. It says find the mode of f of x. So you have this function, and you're supposed to find the mode, the most common result. And again, it's just a definitions kind of thing. So it's not the most obvious thing for you to realize what to do. So here, this is what you do. So the mode is actually the highest point on the CDF graph. So you got to remember like before, right? So we had our graph, and here's all the probabilities. So the highest point here is actually the point where the most sample size was collected. And that's why they know this is the most likely to occur. So that's how you get the mode, right? Because normally mode means most frequent result. And then you think on the probability graph, like, what am I doing with the most frequent result? Well, you find the one with the highest probability, because probability graphs are based on the results in the sample size. So here, to get the mode, we just need to find, you can see here, find the highest point in the CDF graph. So because the CDF graph is a upside down or concave down parabola, it does have a maximum. We just need to determine that maximum. So I'll just show you the working out. So again, I don't feel like talking through the math is that useful. So here is just all the working out. You do it regularly. So here's the original function. And I highly recommend you expand functions out. So you can see like this function is this one. Oh, so that's the, wait, hold on. Oh right, yeah, I already pre-expanded it. So I was like, where did the x squares come from? So I've already pre-expanded to be 3 times x and x times x, and that's where these things came from. And the 2/9 was what we figured out from part one, right? So because previously it was incomplete with an unknown variable p, but now we know that it is 2/9. So I highly recommend you fully expand it out, right? So not just expand out the 3x and the x squared, which I did so instinctively, I didn't even need to feel like writing a second line, but multiply the 2/9 out as well. So now you have these two things here, and it just makes it easier to integrate. Although, so differentiate, sorry, we are differentiating it. Although, actually, you could have just, anyway, well, do it this way. This is the best way. All right, so once you get these two terms here, you can find the derivative, right? So before we were integrating it because we were taking a sum of the area. So now we are differentiating it because we're looking for the rates of change, and very specifically, where the rate of change is equal to 0, because we want to find the turning point of the graph. And that's why you are differentiating the function this time. So when you differentiate it, the 6/9 x is just 6/9, and the 2/9 x squared is 4/9 x. So you multiply the 2 down, and then you bring the power down by 1. So now we need to make f of x. So this is the f dash x, sorry. Now we need to make f dash x equal to 0. So you take the f dash x function and you make it equal to 0, and then algebraically solve for x by adding 4/9 onto both sides, and then dividing both sides by 4/9, and you end up with 0/2, which is 1.5. And 1.5 will be the result that has the highest probability. So while I was running this lesson through with Adrian, I actually took the extra step. I think no, either Adrian or Brooke. I was like, oh, hey, we need to substitute this back into the original function. Like take the 1.5 and substitute it in and find f of x. But you don't actually need to do that because you don't want the actual probability. You want the score, so the value at which the mode occurs, right? So what is the mode? The mode is just the most frequent result. So for this particular distribution, the most frequent result is 1.5, right? So it only exists between 0 and 3, and 1.5 was the most common. It actually has its own probability, which you can find out, but you don't need the probability. You only need to know what is the most common result, and that is 1.5 in this case. So that's that question. All right, so moving on. Next one is a logarithmic question, and it says calculus, but it's got logs in it. And the key part here is just doing the, this is probably not going to copy properly either. I know that's a gray box. Right, so it's actually just a copy paste from the formula sheet. So I just put it here because I didn't want to click back and forth. So let me just replace that. Right, so again, here's what we're working out. But the key part here is actually take this log function and transform it to be two separate functions, right? So there is a thing in the formula sheet that tells you that log base a of f of x is equal to this particular derivative. However, sorry, the question, should have mentioned this at the start. The question is a deriving question. You're trying to find f dash of x. So even though there is a particular thing in the formula sheet about the derivative, this part here, x to the power of 2x, is actually not a function, like not f of x. So you need to use the formula, so you need to use the log laws where you can take the exponent and put it at the front of the expression and use that law, and now you have two separate functions. So you have a function 2x, and you have a function log base 2 of x. And now you can differentiate it. So there are two separate things, so you need to use the product rule. So the product rule in the formula sheet is kind of ugly. It's more formal, but it's a little bit ugly. It's got like du dx and then dv dx and all of that. But the way I learned it back in school was just uv dash plus vu dash. So just faster when you do the writing down. So yeah, you define your two functions. So the u function is 2x, and the v function is log base 2 of x. The derivative of u is just 2, and the derivative of log base 2 of x is where you use this box, right? So we're doing log base a of f of x. So now you do natural log of a, so that's this part here, natural log of 2. And then f of x is just x, right? Because that's the function at the back. And then you put the derivative on the numerator, on the top of the fraction. So the derivative of x is just 1, and you put that on top of the fraction. And then once you have that, you do uv dash plus vu dash, write out the expression, and do some canceling. Now, just be very careful when you cancel. So before, I didn't actually have these brackets here, and it was very tempting to just like cross off this 2x and this 2x. But you got to realize that makes no sense because it leaves you with 1 over natural log of nothing on the bottom. So that's not a thing, right? So the 2 here is not a real number 2. It's a number that you're taking the logarithm of. So don't cancel that, but you can cancel the x though. So you can cancel out the x's, and that leaves you with this option here. So 2 over natural log of 2 plus, and then the thing at the back, which is this here. Right? So that's that question there. Moving on. Scroll down. Here we go. So this question is, again, quite interesting. It's an exponential growth question, or more specifically, exponential decay. So it's got t is equal to 25 plus 70 outside of 1.5 to the power of minus 0.4t. So it's kind of like ae to the kt, except they're not using e, they're using 1.5. And they do have a k value. The k value is negative 0.4. So you know that this is decaying as opposed to growing. So the actual question is not so bad. I might actually not do this in full. Let's see. All right, so here is the working out. So if you, because this is a YouTube video. So if you would like to have a look at how this is done, maybe you'd like to pause the video. I'm not actually going to talk through it too much. But just the key here is deriving the original formula correctly. So we need dt. That is super gross. Why did they use two different letter t's? So the capital T is the temperature and the lowercase t is the time. So you're finding dt. That's so gross. So you're using the one where it's a to the power of f of x. So the f of x here is negative 0.4t. But again, not f of x, we're taking f of t because it's dt. So when you do the formula, it's just about, so a is your base. So the base here is 1.5. So you take the natural log of 1.5. And then this part here, f dash of x, a to the f of x. So you do write the original function all over again, right? So you can see a to the f of x here, a to the f of x here. So whatever you're deriving, you write it all over again, which is here. And then where this negative 28 comes from is this 70 multiplied to this 0.4. So you just like they say, you take the derivative of the exponent. So the derivative of the exponent is just minus 0.4, and you multiply it to whatever was already here, which was 70 1.5 to the power of 0.4. So you did actually write the 70 again, but you just merged it with the 1.4, multiplied it together to become negative 28. So that's where that negative 28 comes from. But the rest of the working out is pretty straightforward, just a lot of substitution. So if you'd like to see how that's done, just give it a pause and try to read through the working out. And moving on. All right. So we have stormwater and tanks and flowing and changing of rates and all that kind of stuff. So I'm just going to copy over the solution and we'll just chat about it. So, all right. So with this particular one, I guess the key part is all these things on the left. So knowing that when you do, so we'll read the question. So water flows into a 7,000 liter tank at a certain rate, and they give you the rate. So the rate again is a concave down parabola. And so the rate itself is like going up and then going down, which is kind of unusual. So it must mean the tank has kind of an unusual shape. It fills up faster than it fills up slower. So just some key considerations here, which is you can see part one. At what times is the tank filling at twice the initial rate? So before you can figure out what is twice the initial rate, you need to know what is the initial rate. So when you want to know the initial rate, you substitute t to be 0 in the function. So I was chatting about this with Adrian, and sorry, Adrian, to call you out here, but he said that, oh, I'll take the function and I'll make it equal to 0. And that's a pretty common misconception, actually. But for this one, you don't actually want a rate of change of 0. You want to know what is the rate of change at a time of 0. So that means you actually swap out the t, which is time, for the number 0. So you get an initial rate of 120. And when you double that for twice that rate, it is now 240. And then we can actually solve for the rate of change being 240. So this is where you do make the dv dt equal to 240, and then you write the rest of the right-hand side equation. And this is just a monic quadratic. So solve it the way you solve a quadratic with PSF. So after you get everything to the left-hand side, so it's actually okay to turn the negative into a positive. So even though we are solving for an upside down parabola, but all we really want to find is the roots. We just want to find where it's equal to 0. So you don't have to keep it negative. So the best way to do it is actually get everything to the left-hand side, so it's a positive parabola, and then you solve it regularly with PSF. Two numbers that multiply together to give positive 120 and add together to give negative 26. So usually you work with the factors first. So 120, 20 plus 6 is 20 times 6 is 120. And then how do I make them negative 26? Well, you make it both negative. So it's so the t is at 6 and 20 minutes. right? So normally, so try not to be trapped by this question. So you can see at what times it's got an S on the end of time. Because normally when you do this kind of time stuff, there's only one time. So this is actually a bit unusual. There are two separate times when it's filling up at double the initial rate. For the second part of the question, find the volume of water. Just got to realize that volume is the integral of the rate of change. So, and then just integrate it. So again, this is like more of a definition thing. If you realize this definition, the actual maths is not horrific. So you just integrate the rate of change function by moving everything up a power and then dividing by that number. All right, and but the plus C is quite important, right? So when you take the integral, there is a constant of integration, and a lot of times it just gets left out because when you're taking definite integrals, usually you don't care about the plus C because you're doing one thing, take away another thing, and the plus C gets subtracted anyway. But for this question, the plus C is very important, so make sure you don't leave that out. You will see in a second, because for part 3, you actually have to find out the C. So they give you the information of initially, the tank contains 1,500 liters of water, and that is your plus C. Right? So initially at t equals 0, v equals 1500. So once you put these numbers, I mean, v is just straight up 1500, but you want to see how mathematically you get there. You swap all these t's for zeros, which makes them all 0, and then you put 1500 on the left-hand side and c on the right-hand side. So you end up with c equals 1500. So now that you have a complete equation, because you got to remember before, this volume equation was not complete. It had a constant of integration you did not know. So at the start of part 3, they gave you enough information for you to figure out what the constant should be. So the constant is 1,500. Now that you have the entire equation, you can substitute 30, which is part of the question, 30 minutes after it began. And then you get the volume that went into the tank. This specific question asks you for the overflow. So the tank is 7,000 liter capacity, so 800 liters overflow. That part's, not even maths. Like you can see, we didn't do 7800 take away 7,000 or anything. It's barely maths at this stage. But it's more of a conceptual understanding one. And that's it. Oh no, there's another one. It's really long, so I might just wrap it up here for today. I'll show you the question though. So if anybody wants to see this question explained, so here's the question. So I guess you can look at this question while I do my outro spiel. So thanks everybody for watching this new teaching video. And yeah, if you have questions, please leave it in the comments or get in touch with me. Or if you have any feedback on this teaching series in general. Last week I got do less calculations. So I'm doing less calculations this week. So with this particular question, right? So hopefully you're reading it on the screen. Hopefully you can see it through the bad resolution. But it's maximization. And the hard part about maximization questions is just getting the expressions that they want. So give it a go yourself. If you are still confused, let me know. And then I might cover this at the beginning of the next video, if it's still going to be on maths. I'm thinking I might switch back in English. We'll see how what the different students request. But yes, thank you for watching this Tuesday teaching series on Thursday. If I get it uploaded in the next 8 minutes. And yeah, and I'll see you in the next one. Until then, keep learning and take care. Always takes an extra 10 seconds to find the stop recording.